Alright, so in the last class we saw that the eigenstates of operators with continuous eigenvalues are Dirac orthonormalizable, and we saw two examples of this. Very briefly to recap, one was the momentum eigenstates, which can be written like this. So you have the momentum operator acting on these momentum eigenstates, and the eigenvalue is p, and here you have the momentum eigenstate again. So this is the eigenvalue equation of the momentum operator. Okay, and we saw that these eigenstates are are Dirac orthonormalizable, which means that you have this relationship p prime p. If you just take two of them, the scalar product of two of these eigenstates is delta p prime minus p. So this is the property of Dirac orthonormalizability. Alright, and we also saw that as a consequence of this Dirac orthonormalizability, the states are complete, which means that you can express any arbitrary state psi as a linear superposition of these p's, these momentum eigenstates. So in other words, it's going to be integral c of p dp. So that means we are taking each eigenstate, giving it a coefficient. That coefficient is c of p dp, and then adding them all up. Right? The analog of this, if we had discrete eigenstates, would be a sum. So we would say c1 1. I mean, it would be a sum like this: c1 1 plus c2 2, and so on. So if the eigenstates were discrete, but they're continuous, they're labeled by this continuous label p, so the c1 and c2, these coefficients, they just become c of p dp. All right. Okay, and how would you find the c of p? Like, suppose you're given a state psi and you want to write out this expansion. You want to know what is the c of p. We saw that c of p can be easily found by taking the dot product of that particular p with psi. You get the c of p. All right, and then one more thing we saw, that now these, when I write a p like this, this is an abstract state. There is no formula for this p. It just refers to the state, the eigenstate p, eigenstate characterized by momentum p. Now, but you can go to different bases and you can write formulas for these states in different bases. And we only looked at the position space. One particular base is called the position space. And in the position space, this operator, this eigenstate, is given by this relationship. So in the position basis, it's psi p of x, and the formula that we got was 1 over square root of 2 pi h bar e to the power of I p over h bar x. So this is in position space. And notice that I did not put an equal sign between the ket p and psi p of x, because they are not really equal. Psi p of x is a representation of the ket p in a particular basis, in position space. All right, so then we also went ahead and did something very similar for momentum eigenstates, or eigenstates of the momentum operator. Sorry, position eigenstates, eigenstates of the position operator, position eigenstates. So here is the eigenvalue equation. X acting on a particular eigenstate y is equal to y, which is a specific position, times the eigenstate y. So these eigenstates are characterized by their eigenvalue y, right? Okay, so these eigenstates are also Dirac orthonormalizable, which means that y prime y is equal to delta y minus y prime, or y prime minus y. We proved this. And they're also complete. Whenever it's Dirac orthonormalizable, it's also going to be complete, which means that any arbitrary state psi can be written as an expansion. So I'm going to call this C of y, y dy. So this is exactly analogous to what we have for the momentum eigenstates. So you can expand the state psi as a linear combination of position eigenstates as well, because they also form a basis. Okay, and how would you find the C of y? The C of y is just is just y, the scalar product of y and psi, your arbitrary state psi. Okay, my psi is looking a bit wonky here. There. All right, and also we had seen the position space representation of the get y. So in position space, get y is represented by psi y of x, and we saw what this function is. It's just the Dirac delta y minus x. Okay, all right, and we derived this in class. Okay, all right, so that's a quick recap of what we did in the last lecture. Now let's talk about the generalized statistical interpretation. We discussed this in the last class, but I just want to go over it again and maybe work through a few examples so that it's clear. Statistical interpretation. All right, so this is, I'm pretty closely following Griffiths here, though my notation is slightly different, but it's more or less what Griffiths has. So it basically says that if you measure an observable A on a particle with state psi of t, so if you measure an observable A, you can think of A as being energy, momentum, angular momentum, position, anything that you can measure on a particle in a state psi x t. The particle is in this particular state. You are certain to get one of the eigenvalues of the Hermitian operator A hat. To get one of the eigenvalues of Hermitian operator A hat. So any observable A has to be represented by a Hermitian operator A hat. Okay, now it's possible that the eigenvalues of A hat could be discrete, in which case we call it a discrete spectrum, or they could be continuous, in which case we call it a continuous spectrum. Both are possibilities. So if the spectrum of A hat is discrete, then the eigenvalue equation will look like this. Eigenvalue equation will look like this. A hat acting on the eigenstate an, and the eigenstates are characterized, eigenstates and eigenvalues are characterized by a discrete index an. So that is the eigenvalue equation. N is 1, 2, 3, 4. N is equal to 0, 1, 2, 3, 4. It might be that n is equal, starts at 1. It depends on the problem. It either starts at 0 or 1. So if the spectrum of A is discrete, the eigenvalue equation looks like this. Now, according to the general statistical interpretation, let's just call this GSI. According to the GSI, the probability, so when you measure the operator A, you're guaranteed to get one of these values, one of these eigenvalues. You're absolutely guaranteed to get one of these. Now, there are many eigenvalues here. Which one are you going to get? Now, quantum mechanics gives you a probability distribution. So the probability, and that's what the GSI tells us, the probability of measuring, or I should say getting the measured value an is Cn square. And what is Cn? Cn is this quantity. So I'll just put the Cn over here. It's take the state an and find its scalar product with the state of the particle psi. That is the Cn. And square it, I mean take the complex conjugate square of it, that will give you the probability of getting the measured value an. So you know these eigenstates an, and you know the state the particle is in. So the state the particle is in, I'm just going to call this state as psi, like this. All right, so the particle is in a state psi in general, and you know the eigen states of this particular operator A. So according to the general statistical interpretation, when you make a measurement, you will find the particle in one of these eigenstates. So that's called the collapse of the wave function. The wave function is going to collapse and you'll find the particle in one of these eigenstates, and you're going to measure the eigenvalue an. And what is the probability of measuring a particular eigenvalue an? The answer is just take the scalar product of the eigenstate an with the state of the particle before you made the measurement, and complex conjugate square it, and that will give you the probability of finding the particle in that particular state and measuring that particular value of the operator. So that is what happens when you have a discrete spectrum. Now, if the spectrum is continuous, so suppose A is position or momentum. These operators have continuous spectrum. It's continuous. Then the eigenvalue equation would be A, and so now I'm not using a discrete index to label the eigenstates. A. So A is the eigenvalue and it's a continuous number, and so I'm just using A to label the eigenstates. So this is very similar to how we used the momentum to label the momentum eigenstates, or position to label the position eigenstates, because these are continuous quantities. All right, so I'm just using a more general operator A. Okay, so now the GSI says that if you make a measurement of whatever this quantity A corresponds to, you will get a measured value of A. But what is the probability of getting a particular A? Now, since A is a continuous variable, you can't really talk about the probability of getting a particular value of A. You can only talk about the probability of measuring something that lies in a range, of A lying between a range of A to A plus dA. So the probability, that is because A is a continuous variable, probability of getting a measured value between A and A plus dA is the following. It's very, very similar to what we had before. The probability is always a probability density multiplied by a range. So the range here is just dA. So the probability is going to be C of A squared dA. So notice the similarity with the discrete case. There the probability was Cn squared, just Cn squared. But here the probability is Ca squared dA, because you cannot talk about the in the discrete case you can talk about the probability of finding the system in state n, but you cannot really talk about the probability of measuring the value at A with infinite precision. So when you're measuring a continuous variable, you can at most measure it within a certain range, A to A plus dA. So the probability of measuring the value of getting a measured value that lies in the range A to A plus dA is given by Ca squared dA. So Ca squared is our probability density and dA is the range. Okay, and now what is that going to be equal to? It's exactly similar to what we had before. The Ca is just obtained by taking the scalar product of the eigenstate with the state the particle is in. So when you make the measurement of the operator A on the state, you're going to get the system will collapse into this this state, which is the system is going to collapse into the eigenstate A, and the probability of measuring an eigenvalue between A and A plus dA is this thing squared dA. So that is the general statistical interpretation. Okay, so let's look at a few examples of applying the general statistical interpretation of quantum mechanics. So we'll start with the example of a particle in an infinite square well. So example 1. So suppose we have a particle in an infinite square well, and the particle is initially in state psi. So that's the state of the particle initially, before we made a measurement. Now in position space, this state can be represented by the position space wave function, which we are quite familiar with. So psi of xt is equal to summation n equals 1 to infinity Cn psi n of x t of t. So this is the position space representation of psi, of the state psi. Okay. Now the Hamiltonian operator has the following eigenvalue equation, which I'm going to write in basis free language first. It's going to be eigenvalue equation will be H acting on the state n produces En is equal to En times the state n. So I'm writing this in basis free language. I'm representing each eigenstate by the ket n, but we know that we've solved this problem in position space. So we know that in position space the ket n is represented by psi n of x, and you know exactly what this is. If the width of the well is L and it goes from x equals 0 to x equals L, then the psi n of x's are given by sine n pi x divided by L. Alright, so you know this very well. So that is the position space representation of the ket n. Okay, another thing that we know is that these eigenstates, the psi n's, are also orthonormal, which means that if you do psi n star of x, integral psi n star of x, psi m of x, and you integrate, x is psi's are only non-zero between 0 to L, so you just integrate from 0 to L. This is equal to delta mn because they're orthonormalized. Okay, now we're going to follow the GSI recipe. GSI means General Statistical Interpretation, recipe of calculating the probability of measuring an energy En, which means we want to find the probability that the particle lies in an eigenstate, in the particular eigenstate n. So that probability is going to be P of n. So according to the general statistical interpretation, that probability is just the square of this quantity, and this quantity is called Cn in general, and it's equal to the product of the particular eigenstate whose probability you're calculating and the state of the particle. So this will give you the probability of finding the particle in state n. So this is the probability of finding the particle in eigenstate n and measuring. If you find it in eigenstate n, you will measure the energy En. Right? All right. So how do we evaluate this? So let's evaluate this in position space, because that's the one space that we're quite familiar with. So this dot product, so I'm going to keep these bars outside. This dot product is just going to be psi n star x, and then the psi, I'm just going to plug this in. So I'm going to plug this in. So the psi is going to be the summation. I'm going to use a different index because n is a particular index that I'm interested in working with. The summation index, I'm just going to call it m or something. M goes from 1 to infinity in this case. Did I do 1 to, yeah, 1 to infinity. Cm psi m of x t of t. Okay, and let's just put this in a square bracket. That's the psi of xt dx. So I'm taking the scalar product of psi n of x, but I'm also put in the expansion for. So I'm taking the scalar product of psi n of x and psi of x and t, and I just put that in there. So maybe I should just write this as well. So it would be integral psi n star of x, capital psi of x and t. So that's what I'm evaluating, dx squared. That's the thing that I'm evaluating. And in the next step, I just inserted the expansion of capital psi xt. So this summation, this integral is not hard to do. So this would just be, I can just pull the summation outside, m equals 1 to infinity, and then I have the Cm psi n star x psi m of x dx and move the integral inside dx, and then that's it. I think, oh, and there's a t of t. The t of t does not depend on x, so I can just pull that out of the integration. Okay. All right, so what is this quantity? Since the psi n's are orthonormalized, we get m equals 1 to infinity Cm delta mn multiplied by t of t squared. All right, so what is this sum going to be? Delta mn is only 1 for n when m is equal to n, and it's 0 when m is not equal to n. So there's only one term that's going to survive from this sum, and so that's just going to be Cn multiplied by t of t squared, complex conjugate squared. Now what was the t of t? So we know the t of t very well. It's just e to the power of minus I en divided by h bar times t. So that's our t of t. And so when you take a complex conjugate of that, it's just going to become 1. So the answer is just going to be cn squared, and that's exactly what we expect in this case. So we know that the probability of finding the particle in a particular eigenstate is just this coefficient cn complex conjugate squared. So we'd seen that earlier. So the general statistical interpretation tells us what we expect. All right, now let's do another example. So let's look at the probability. So you have some particle in state. So this is example 2. You have a particle in state psi. Particle in some general state psi. And you want to find the probability of finding the particle. You're measuring the position of the particle. So this is position measurements. You're measuring the position of this particle. What is the probability that you'll find the position to be between y and y plus dy? So probability of finding position, of measuring the position to be between y and y plus dy. As I said before, for a continuous variable, probability of measuring the position to be exactly y up to infinite precision is going to be 0. You can meaningfully talk about measuring the probability to be within a certain range. And so we're making this range infinitesimally small. So we're saying, what is the probability of finding the position between y and y plus dy? So let's just jump straight to the general statistical interpretation and see if we get a sensible answer. So the general statistical interpretation says that the probability of measuring the particle's position to be between y and y plus dy is just going to be this quantity squared times dy, and so that's just going to be, so cy is just the overlap or scalar product. Scalar product is sometimes called overlap of the eigenstate y with psi. So this y, these y's are the eigenstates of the position operator. So that's exactly what we did before over here. We took the scalar product of the eigenstate with the state in which the particle was before making the measurement. That's exactly what we are doing over here. Now again, we will evaluate this product multiplied by dy. So we will evaluate this in position space because that's the space that we are familiar with. So in position space, this scalar product becomes, you would take the position space representation of y, of eigenstate y, which we've done before. Oh, that was a different document. We know what that was. That was psi y x. But since we are taking a scalar product, we have to star this. The position space representation of the state capital psi is just the position space wave function. All right, and so the scalar product would just be this quantity integrated from over x minus infinity to plus infinity, and then that's it, and square that dy. That should give us the probability of finding the particle between y and y plus dy. So that's what this thing should turn out to. And so let's evaluate this integral. This quantity, we know what it is. We worked it out in class. Minus infinity to plus infinity. It's just delta y minus x, and the star doesn't matter because the delta function is real. Psi of xt dx square dy. And now what is this going to be? This will just be psi of yt, absolute squared, absolute value squared, complex conjugate squared, I mean. And see, this does make sense, right? So we had learned earlier in the beginning of the course that if you want to find the what is the interpretation of the wave function of a particle, the complex conjugate square of the wave function gives you the probability density of finding a particle between y and y plus dy, and that's exactly what the general statistical interpretation is telling us. All right, so that concludes this example. Now let's do one more example. The question we are asking is, what is the probability, so this time we are making a momentum measurement. So example 3, momentum measurement. So the question we're asking is the following. We have a particle that's in an arbitrary state psi. Our question is, what is the probability that when we make a measurement of the momentum will lie between p and p plus dp. This is the initial state. What is the probability of measuring, or I should say, what is the probability of measuring the momentum to be between the value of p and p plus dp. And once again, momentum is a continuous variable, so it does not make sense to ask what is the probability of measuring the momentum to have this particular value, because you will not be able to measure the momentum to infinite precision. So you have to you can only talk about a range. So what's the probability of measuring the momentum in the range p and p plus dp? So we are going to use the general statistical interpretation to answer this question. So according to the general statistical interpretation, the probability will just be, it's the same pattern, C of p square dp. So that's what the answer is going to be. And this C of p is just the scalar product of the momentum eigenstate. So we are asking what is the probability of finding the particle in this momentum eigenstate p. So all you have to do is take the scalar product of p and psi square dp. Now again, we will evaluate the scalar product in position space. So evaluate in position space. And so this will be equal to this product. You have to use the position space representation of eigenstate p and also the position space representation of the state psi. We know both of these. So this is going to be psi p star x. So we'd work this out, the position space representation of p. We'd work this out in class. And I put a star because we are taking a scalar product. And then the position space representation of the state capital psi is just the position space wave function, which is psi of x t. That's it. And then we have to do an integral minus infinity to plus infinity over x, and that is the scalar product square dp. All right. So what is this going to be? So we know what the psi p of x is. So we know that psi p of x, or I should just write this over here. So the eigenstate p in position space is represented by psi p of x, which is equal to integral, which is equal to not integral, sorry. It's going to be, we worked it out, it's 1 over square root of 2 pi h bar e to the power of I p over h bar x. So that's what the ket p is in position space. So I'm plugging that in over here. So this will be, since it's starred, I'll have to put a minus. So 1 over square root of 2 pi h bar integral minus infinity to plus infinity, and then e to the power of minus ip over h bar x and psi of x t dx. Okay, squared dp. Now let's look at this integral carefully. What does this remind us of? You have a function psi, just forget the t dependence, you have the function psi of x, and you are multiplying it by 1 over square root of 2 pi h bar and e to the power of minus p over h bar x. So this is exactly a Fourier transform, right? So what we're getting over here is just the Fourier transform of the position space wave function, and we have seen this before. This is nothing but the momentum space wave function. So we call this integral as phi p of t. When you take a Fourier transform, it's just going to depend on p, it's not going to depend on x anymore because you're integrating over x. So we call this quantity inside the integral as the momentum space wave function. And so essentially momentum space wave function dp. So the probability of the momentum lying between p and p plus dp is just the momentum space wave function squared times dp. And so that's it, and that's exactly what we would have expected, and that's what the statistical interpretation is telling us.